Hi everyone, here's some optional but cool notes about conic sections. We're going to talk about some cool properties here. Now, let's go back to talking about parabolas. And let's talk about the locus or geometric definition of a parabola. Before we've talked about the locus definition of a circle, a set of points equidistant from a fixed point called the center, and the locus definition of an ellipse, where we consider the set of points whose sum of distances from two fixed points called foci, that sum remain the same, a constant. But what's the locus or geometric definition of a parabola? Now, an ellipse had two foci. A parabola has one focus. And we also need to talk about another line called a directrix. So for example, here's our old friend y equals x squared, a parabola opening upward, the classic one. Now, a parabola consists of all points that are equidistant between a fixed point, called a focus, and a fixed line, called a directrix. So for example, consider this point on the parabola, y equals x squared. The distance between this point and the focus is equal to the distance between this point and the directrix. These distances are equal. The parabola here consists of all points that have equal distance from the focus and from the directrix. Now, if you look at y equals x squared itself, right, the vertex is at the origin. The vertex is the most special point on the parabola. The vertex is the point that's closest to the focus. The vertex has distance 1/4 from the focus. So the focus here has coordinates 0, 1/4. Again, that's for the parabola y equals x squared specifically. And since the origin here, since this vertex has to be equidistant from both the focus and the directrix, that means that the directrix has equation y equals -1/4. That's true for the parabola y equals x squared. Let's consider a more generally shaped parabola. Let's consider y equals ax squared, where a is positive. So for this parabola, the focus is 1/4a units away from the origin here, the vertex. The directrix has equation y equals the opposite of that number here. So that's the locus definition of a parabola. Now, more interesting actually is there's a video here, not mine, which describes how to construct a parabola using these ideas. Now, even more interesting though, is the idea of reflecting properties. What is the reflecting property of a parabola? So consider this parabola. It has a fixed point called the focus, and here's the reflecting property. Let's say that light rays emanate from the focus. Here's a focus F. Let's say that light rays emanate from the focus, like so. How do the light rays reflect off of the parabolic surface here? They reflect off in parallel rays. The light rays reflect off the parabola in parallel rays. Now, if you take a parabola and you revolve it about an axis, you get something called a paraboloid. That's the three-dimensional analog of a parabola. And guess where you see these things on your car? If you are still using your car. Not funny. Where do you see paraboloids on your car? How about headlights? This property allows the headlight to shine as brightly as it can, since the rays of light from the focus, they're being reflected off in parallel rays. That's kind of the idea. Now, what's the corresponding reflecting property for ellipses? Right. Well, if you enjoy playing pool or golf, then you love ellipses. So imagine that you have a perfectly frictionless surface and a perfectly elastic boundary that's elliptical. So let's say that you're playing pool or golf. Let's say golf, miniature golf. How can you impress your friends who don't know math? Well, you can put the hole on your little miniature golf course at one focus of the ellipse here, this elliptical playing field. And then you put the ball at the other focus. And the idea is that regardless of which direction that you hit the ball in, right? Regardless of which direction you hit the ball in, if the ball reflects off that elliptical surface, is perfectly elastic here, right? It's going to fall into the hole. So if the ball is at one focus, it'll reflect off the ellipse, and the ball will fall into the hole here at the other focus. Now, this has many applications. This reflecting property for ellipses has a lot of great applications. Again, this is for ellipses, of course. In fact, John Quincy Adams, the former president and congressman, John Quincy Adams, when he was in Statuary Hall in the U.S. Capitol, he would eavesdrop on his political rivals by basically standing, by basically telling his rivals, "Hey, why don't you stand over here? It's a nice view and all." So his rivals stand over here, and then at one focus, and then above the other focus, he might be standing on a part of balcony above the other focus. He'd be able to hear the conversations of his rivals better because of the reflective properties of this elliptical boundary. Okay, a Statuary Hall was elliptical in shape. So his rivals would talk basically at this point. He'd be up in the balcony, maybe over this focus over here, and he could hear his rivals pretty well, eavesdropping. That's pretty cool, but there are actually serious medical applications as well. Something called lithotripsy. Lithotripsy. Lithotripsy is used to destroy kidney stones. The idea is that your kidney stone is placed at one focus for this elliptical boundary, and then sound waves emanate from over here, reflect off, hit the stone, and break it up. It's a very non-invasive way of breaking up kidney stones, and this is used, lithotripsy. Ellipses, by the way, have other very important applications. For example, you're standing on one. The Earth. Kepler's laws of planetary motion, 1609. Johannes Kepler. He was the one who said that planets revolve around the sun. And that in and of itself was a controversial idea, right? We got that from Copernicus as well. Planets revolve around the sun with the sun at one focus of an elliptical orbit. Planets and comets go around the sun in elliptical orbits with the sun at one focus. And by the way, in terms of velocities through space, planets sweep out equal areas in equal time. So if the planet is close to the sun, then it moves faster. If the planet is far away from the sun, it moves slower. Bear in mind, for this kind of eccentric orbit, the planet's going to be a lot colder out here than over here. Okay, the Earth doesn't have quite that level of extremes. We're circular enough. Comets, by the way, can have very eccentric orbits. Okay. Oh, and by the way, they're not just elliptical. There's a study that showed that when you consider comets that were discovered before 1970, about 48% had parabolic orbits, only 40% had elliptical orbits, and 11% had hyperbolic orbits. We'll talk about hyperbolas later on. Halley's Comet has an eccentricity of 0.97, very eccentric. Even more eccentric, Kohoutek, about 0.999925 or something like that. So comets can have very, very, very eccentric orbits, very, very elongated, okay, with the sun at one focus. Right. So it's really quite an event when the comet comes around and meets and comes around the sun, the focus here. Usually it's far away. All right, we'll talk about hyperbolas more later on. But ellipses, a nice reflective property if you enjoy pool, like a pool table, right? A pool ball here, hole here. Really more like golf, miniature golf. Miniature golf is a better example because pool tables don't work like that. Also, if you're eavesdropping, like John Quincy Adams. Lithotripsy, if you have kidney stones, which are painful. Kepler's laws. Planets, comets have elliptical orbits, or conic orbits in general. Ellipses Fortunately, the Earth is on an elliptical orbit. If we were on a parabolic or hyperbolic orbit, I think we're in trouble. We're moving away from the sun. All right. Okay, so we're going to talk more about hyperbolas, these guys, next time, and talk about some of their properties.